Yes, that I think, yeah, it's working now. I'm gonna stop the transcription because we don't want that. And I'm gonna stop sharing my screen. Oh no, first, sorry, I almost forgot. I would like to introduce Paolo Dell'Aversana, our guest speaker today. Paolo graduated in geological sciences and in physics, and he has about 35 years of experience in various areas of the earth disciplines, including geology, volcanology, and exploration geophysics. Furthermore, he's a musician and a recognized expert in sound engineering and audio signal processing. He currently works for Eni as a senior geophysicist, data scientist, and project manager for the development of innovative geophysical technologies and machine learning methods. He's the author of various patents, has published over 100 specialist articles, and several books. He has received also international awards, including the prestigious Eni Award from the President of the Italian Republic as a recognition for innovation. So now I'm gonna stop sharing my screen, and please, Paolo, go ahead with your presentation.
Thank you, Florencia, for your introduction, and thank you, the AGA local chapter, the Netherlands, for giving me this opportunity for presenting this unusual combination between geophysics, sound engineering, digital music, and machine learning. So let me share the screen. Okay. Okay, let me know if you see my presentation, please.
Yes, we can see it.
Okay, I also want to share the sound. Sorry, so I exit from this because I want to.
Yes, take your time.
Yeah, I want to share also the sounds of the. Ok, screen, condividi audio system. Ok, now it should be okay. Okay. Do you see the first slide of the presentation?
Yes.
Yes.
Good. So this is the summary and a few keywords of my talk. Basically, I will talk about analysis, classification, and interpretation of geophysical data after transforming this data into musical formats, so MIDI and audio files, working both in time and frequency domain, and using sound engineering tools and the techniques from musical information retrieval and machine learning algorithms. Motivations. What are the main motivations for this approach? The first very important motivation is that using these methods, we can add a new perceptive dimension in data analysis and interpretation, that is the sound. So we don't change the information. Information is the same as usual, but we add some new additional cognitive possibility, that is the audio. So we can combine audio files and video files at the same time in a sort of dual perception of the geophysical data. And the second very important motivation is that we can include new attributes that are wave, audio, and MIDI attributes for allowing automatic analysis, classification, and interpretation of geophysical data using machine learning methods. Let me explain just in few words the methodology. The first very important step of this approach is that we convert segue data, that that is the standard format of seismic data, into MIDI format. MIDI means musical instrument digital interface. It is a standard digital musical format. And then we extract MIDI features from these converted files. And we can use these features as complementary attributes for data analysis, automatic classification, clustering through machine learning methods. Let me explain what I mean by MIDI feature. MIDI feature is an attribute that we can extract from a MIDI file. This is an example of MIDI file. So what you are seeing, what you are looking at now is basically a seismic trace that is transformed into a MIDI file in the so-called piano roll display. That is a typical display that is used in MIDI music. On the vertical axis, we have the pitch that is related with the frequency of the signal. On the horizontal axis, we have the travel times of the trace. In this case, they are about 3 seconds. And in colors, you have the sound intensity. So blue means low intensity of the sound, and red means high sound intensity. And from this type of MIDI file, we can extract many attributes that are, for instance, the pitch that is related to instantaneous frequency, the velocity, MIDI velocities, that means an attribute related to signal amplitude, patterns and ensembles of MIDI notes, including melodic, harmonic, rhythmic trends, and more complex attributes such as pitch histograms and statistics, note lengths, and many other scalar and vectorial multi-value features. So basically, what we can do is to extract some type of new attributes that have no equivalent in the traditional seismic domain after this segue to MIDI transformation. And we can use these new attributes together with the traditional seismic attributes for many different purposes, including data analysis, classification, and clustering of seismic data. The key idea is that MIDI attributes are complementary to traditional seismic features for characterizing seismic data. For instance, in this display, you can see a seismic trace. On the horizontal axis, we have the time. It is about almost 3 seconds. And this seismic trace was extracted and was calibrated by a well that was drilled, correspondence of a stacked reservoir where we have 2 layers. The first one is a low gas saturated layer, and the second one is high gas saturated sand layer. And in the lower panel, you have the correspondent MIDI file extracted from this seismic trace. So again, on the vertical axis, we have the pitch. You can see a sort of a virtual keyboard on the vertical axis. And the colors mean the sound intensity. And so you can see how we can represent, from a musical point of view, a seismic trace. And in the second part of the talk, I will give you some demonstration of the sound, of the listening of these signals that we transformed from seismic to MIDI. So we can listen to this seismic signal after this transformation. And this transformation offers many benefits because we can use these features for big data mining, for pattern recognition, for data clustering, and automatic classification, because we have a very important benefit. MIDI format does not require high computer memory. A seismic trace is less than 1 kilobyte. And this allows fast data processing and application of many advanced musical technologies for analysis and automatic clustering and classification of the data. And we can apply, of course, both supervised and unsupervised machine learning methods. So the first very important step is how we move from SegWi to MIDI. This is the reference paper that I published with my colleagues that I thank. And for instance, this is a conventional seismic trace in SegWi format. We apply many types of mathematical transforms to this seismic trace, such as Stockwell transform or wavelet transform, in order to extract the spectrogram from this seismic trace. So we have a frequency, time, and amplitude. In this case, we apply the Stockwell transform, and this is the same trace in where the spectrum is displayed in 3D. So we have amplitude, frequency, and time. And after doing that, we apply a nonlinear relationship between the instantaneous frequency and the MIDI notes. So, for instance, in this case, n indicates the sequential number of the MIDI note. For instance, n equal 1 corresponds to the first musical note that we have on the keyboard at about 16 hertz, and so on. So we can basically create a one-to-one correspondence between frequencies extracted from the spectrogram and the MIDI notes. And we create a sort of a discretized spectrogram in terms of MIDI format. So this is the same trace, the same spectrogram, and below you have the MIDI file in the MIDI piano roll display. Every small point in this MIDI piano roll display represents a musical note. So it is a sort of discretization of the spectrogram, but with the big advantage that we can play this spectrogram, this MIDI piano roll display. We can listen to the seismic trace. We can assign any type of digital instrument that we like to this MIDI file, and we can listen to the seismic trace with the piano, with the violin, with the guitar, with everything we like. And furthermore, we have the possibility to extract the MIDI attributes that I have talked about before, and we can use these MIDI attributes for classification with machine learning approaches. After doing that, we can import the seismic file transformed into MIDI files into a digital musical domain. So every line that you can see here is a trace, a seismic trace transformed into a MIDI trace. And we can, so this is a sort of virtual mixer where we can mix the different seismic trace in terms of real sounds, and we can listen to them, we can stack to them, we can filter them, and in theory we can put every type of number of seismic traces that we want to import in this musical domain. For instance, this is the same seismic trace that I showed you before, and below you have another representation of the MIDI trace. It is called the pitch histogram. So here the colors represent the pitch, so the frequency of the signal, and immediately you can appreciate a very interesting aspect of this transformation. You can see rhythmic properties of particular pitches here in this representation, and a big difference between the low saturation and the high saturation part of the signal in terms of pitch histogram. So immediately you can understand that pitch and the rhythmic properties of the signal are important for characterizing the original seismic signal. And the pitch is just one among more than 100 MIDI attributes that we can extract from this signal. We can filter it. In this case, we applied a low pass filter to the pitch histogram in order to highlight the high saturation part of the signal. in blue, we can do many operations in very simple way using the traditional tools that conventionally we use, commonly we use in sound engineering environment. The second part of the job is importing all the MIDI files and the MIDI attributes into machine learning environment. And for instance, here you can see the rhythmic properties, and these rhythmic properties can be quantified using the rhythmic attributes in terms of MIDI features that are used in the machine learning domain for characterizing the data, together with the other attributes. For example, here we have a seismic section where we have four gas sand channels, A, B, C, and D. These are sand channels filled by gas at different level of saturation. And we created a MIDI representation of this seismic section, trace by trace. And in order to characterize the different channels with the MIDI attributes, for instance, let's focus the attention on the channels C and D. These are just four seismic traces in a distance range of about 50 meters, transformed into MIDI pitch display. And so this is depth. So this interval is about 100 meters. You can see how the different channels are represented by different properties in terms of pitch attribute. And remind that pitch is just one among more than 100 attributes that we can extract from this MIDI file. Other attributes are related with the melodic properties, harmonic properties of the signal. And finally, after using all these attributes, we can apply machine learning for plotting on the section the different types of channels that are different because they are characterized in a different way by more than 100 MIDI attributes. So you can understand that we can use these MIDI attributes as a important support, complementary support together with the traditional seismic attributes for classifying and characterizing our seismic data. This is just an example. Let's go to listen to this data, because the other advantage is that we can add a perceptive dimension to the visual conventional dimension. So we can see and we can listen to the same signal at the same time. So let me do some example. Let's start with a very simple example. In this case, in background on the left panel, you have a seismic section. Here we have a seismic trace, just a single seismic trace extracted from the seismic section. This is the MIDI file extracted from the seismic trace using Stockwell transform. This is the wave, the corresponding wave file, and this is the spectrogram. And now we are going to listen to this seismic trace moving from the top to the bottom of this section. This is just a cartoon showing a possible geological model. And we are going to surf on the seismic musical wave, because we are at the same time, we are going to see the seismic trace moving from top to the bottom and to listen to the sound of the seismic trace that is played using an automatic digital piano. So let's try to listen to it. So of course the music is not very nice, but what is important that this music contains a lot of sound information in correspondence of the main discontinuities you can listen to, corresponding discontinuities also in terms of sounds. This was just the simplest case where we performed the sonification of a single seismic trace. In the second example, we again have the sonification of a single seismic trace. In this case, it is an earthquake. So we have the seismogram of an earthquake, and you are going to see at the same time the seismogram of the earthquake, and also you are going to listen to the sound of the earthquake after applying a piano to its MIDI file. And you also will see at the same time the spectral analysis of the frequency content of this signal. So here you have the possibility to see the signal in time domain and in frequency domain, and also to listen to the sound at the same time. Now we move to a more complex example. Here we have an entire seismic section. This is a very long seismic section. It is about 175 kilometers long. It is a very important seismic section because here we have a couple of important oil discoveries. In particular, we have the Skugard discovery, a gas and oil discovery here. And I'm going to show you what is the sound of the oil, what is the sound of the lateral geological change, for instance, moving from year to year when we change completely the geological domain, when we exit from the reservoir, we move in this other area. So you are going to see this yellow symbol here moving from left to right very slowly, and at the same time you are going to listen to the sound of the seismic signal that is encountered by this symbol at this specific depth here. So we are going to listen to the sound at a specific depth. So this is the sort of envelope of the amplitude of the seismic traces that this yellow symbol meets moving from left to right. And this is the corresponding spectrogram from which we extracted the MIDI file that we are going to listen to. Again, the music is not beautiful, but please pay attention on the sound variations when we move from a particular image domain to another, in particular when we are in the gas oil reservoir here. So let's go to listen to the sounds. It should start in a few seconds. Okay, I stop here. The message should be clear. Basically, we have different sounds and different media attributes in different geological situations, in different fluids situation, different scenarios, and we can quantify all these differences, also including the differences that our listening is not able to capture, because we can use machine learning methods such as deep neural networks for capturing all the minimum variations in terms of media attributes for classifying the different scenarios. This is the sense of our approach. Basically, it is a multimodal approach where we can see the traditional seismic section in time domain or in depth domain. We can see the spectrogram representation of every small part of this section, and we can see the media representation, so the musical representation of the same signal, and we also can listen to it. So it is a multimodal representation of the same signal. We don't change the original information of the signal, but we amplify, we expand the possibility to have a different perception and a different cognition of the same original signal. This is the message. And the last example is faults. Applying the same approach that we have seen before, we can move from left to right along a given seismic section, and at the same time listening to the sound of the faults and to see the faults in terms of spectral variations. So this is in the lower panel, we have the spectrogram of the faults at a given depth of a seismic section. And here we have also the possibility to see the spectral variations over the time. And we can listen to the sound of the faults. In this case, I assigned a particular MIDI sound to the faults in order to amplify the listening effect of the faults that you are going to see. So basically, you have the possibility to capture at the same time with a dual sense perception all the lateral variations and discontinuities that your mouse meets along the section at a given depth. And you can see the signal in time domain, in frequency domain, and you can listen to it. This is the main message. So I think that we can come to the main conclusions. We have applied this method to many seismic data, and using our machine learning platform for trying to classify in automatic way our seismic data, trying also to distinguish very difficult scenarios that in general cannot be distinguished by using conventional seismic attributes, such as the low gas saturated sands from high gas saturated sands. And there are several papers that we published on that. I'm going to give you some crucial key references that you can find in the scientific literature and you can download for free. And the MIDI features, many MIDI features have no equivalent in the seismic domain. For instance, all the MIDI features that are associated with the rhythmic or melodic or harmonic properties of the seismic data have no equivalent in terms of conventional seismic attributes, and they can be used as a complementary support in the process of automatic classification and interpretation of the seismic data. The good news is that our approach is fast and accurate at the same time. In fact, when we produce the MIDI display from the spectrogram, we create a discretized representation of the spectrogram. That's true, but it is extremely detailed, and we lose about 3 or 4% of the signal when we do this transformation. And the part that we lose in general is associated with the noise. So we preserve the main part of the signal. This is due especially, this is because especially uh, of the, thanks to the mathematical transform that we use, that is the Stockwell transform, that is very accurate for this type of purposes. The other benefit is that the MIDI files require very small computer memory for storing all the relevant physical information of the original signals, including but not exclusively seismic signals. We can apply the same approach to every type of time series, including other types of geophysical signals, such as electromagnetic data, for instance, or also to well logs. We have applied the same approach also for transforming resistivity or sonic logs into MIDI files and going through the same machine learning approach. These are some useful references that we have collected over the years, and you can find all these references on ResearchGate or on Geophysical Prospecting or First Break, the leading edge, and main, the main part of these references can be downloaded for free. If you go to my ResearchGate page, you can find them. And also there are YouTube references and books where you can find many other audio files, including the audio files that you have listed to in this presentation on my YouTube channel. And also there are a couple of books published with Elsevier, with Academic Press, with Cambridge Scholars, where you can find additional details on this approach. And this was the last slide. I really thank you for your attention. And if you have questions, please do not hesitate to ask me.
Thank you so much, Paolo. It was a very interesting, a very creative way of like looking at seismic data in a different way and getting new attributes. So we have a few questions in the chat. Let me go. Yes. So we have the first questions from Roderick. The first question is it any advantage to transform the seismic data, the seismic trace into MIDI format instead of keeping into as a time series compute the same attributes? Sorry.
Yeah, there are two main advantages. The first one is that when you transform into MIDI format, you can listen to the signal. Instead, if you stop at the time series, you cannot listen to it. So if you want to listen to the seismic trace or to the seismic data, you have to transform it into a musical format that you can import into a musical software that is commonly called a sequencer. And after doing that, you can listen to the signal by assigning a piano, a violin, a guitar, everything you like to your signal. Depending on the instrument that you assign to the signal, to the time series after MIDI transformation, you can highlight specific components of the signal, focusing your attention on listening high frequencies or low frequencies during the listening. And this is an additional perceptive dimension that you add. The second advantage is that when you transform into MIDI format, you can take benefit from the huge amount of engineering tools that are available in the sound engineering domain. Many of them are for free. You can find them for free or at very low cost on internet, and you can apply musical information retrieval techniques that are based on MIDI and audio formats. So these are the main benefits that you can take after transformation of signals and time series into MIDI.
Great. Another question I think is just related to the last part that you commented about all the resources in like music signal processing. So do you recommend any Python library to convert the seismic form segue to MIDI format?
Yeah, you can use Librosa. Librosa is a Python library that deal with the wave, audio, and MIDI files. And also there is Pi Music. It is another big library of musical algorithms dealing with geophysical signals, but also with every type of time series. And yes, there is a lot of material in terms of Python libraries on the web. Basically, yes, we use the not only public Python libraries, but also proprietary algorithms. And if you are interested in the mathematical and physical details of our approach, you can see one of the main papers that we published, in particular the one that was published on geophysical prospecting a few years ago in 2016, I think.
Great, thank you. And then the last question from Roderick is, in terms of size, yeah, you mentioned a bit of this, how the MIDI format compared to the standard segue, or treat the seismic as a NumPy array?
You mean in terms of sites?
Yeah, I thought the first part of the question maybe like in terms of the size,
yeah,
maybe memory-wise, but then it also says
yes.
as a NumPy array. Yeah.
Yeah, the MIDI files are a little bit less computer demanding, memory demanding than a segue, because we exclude some part of the signal after the discretization. So it is a sort of, let's say, compression of the data, but the size is a little bit smaller, depending on how we apply the transformation. We have many options in our software, depending on how much part of the signal we want to preserve. If we know the highest part of the signal is high frequency noise, we can apply particular type of Stockwell transform in order to exclude the high frequency content, and so the final result will be a less memory demanding product with respect to the segue.
Great. Well, I hope that answered Roderick questions. And then we just have a comment from Edward that said that he liked the music, the sounds in, like, I think it was in the image with gas.
Okay.
And
Yeah,
we saw
yeah,
him
yeah.
dancing to it. So he was quite enjoying it. And then we have a comment from Andres Chavarria. Thanks for sharing the material. I work with distributed fiber optics, sensing data where we can interrogate fibers to 100 kilohertz. I can envision this methodology useful for downhole surveillance. I don't know if you have a comment on that
Yes,
part.
yes, this is a very important point. In fact, I have been contacted several times by different service companies working in the same field of fiber optics in the past, because this type of methodology can find an interesting application in analyzing fiber optic data. Uh, and some people are thinking about that. Uh, After transforming the huge amount of data collected by fiber optics into MIDI files, of course, you will lose something, but you will have a quite powerful method for analyzing huge and big data, also from a listening point of view. This can be very useful, especially for borehole applications, but not only for borehole applications. Coming back to the comment about the sound of oil and gas, that was a very good comment, because indeed the most interesting part of that section is when the yellow circle crosses the screw guard discovery, and at that point you can listen to a completely different music. It is not a beautiful music, but it is very different from what you have on the left and on the right, and that is the effect, probably, this is my interpretation, uh, the effect of oil and gas, of the different fluid saturation in that specific area that is very well calibrated by the wells. So we have the sound that is calibrated by the wells, and this is the reason of my personal interpretation. It is supported by a borehole calibration. And you can listen to that section again whenever you like, going to my YouTube channel, because it is reported in that channel.
Nice. Yeah, I have actually a question before I continue in the chat regarding that, because then in the one that you showed with the fault, you mentioned that you assigned a specific sound to the faults. But
Yeah.
how did you do that? How do like it was an attribute that you saw and you assign a
No, it is.
specific
It is a.
sound?
No, it is. Let's say the unique choice of the user. Uh, after transporting the MIDI files into the musical environment, you can select by yourself. I mean, the user can select by itself um, a particular sound among a big library of digital sounds that are included in the software. There are many thousands of sounds, including the different types of piano, different types of guitar with different effects. You can select what you like for highlighting some aspects of the signal that you like. In the case of the faults, I selected um, a, a sound that is called glass. In fact, it is the sound of a glass that is cracking, a crashing glass. And it is, of course, a subjective choice of the user. It is not an attribute, because the attributes are objectives. Uh, um, Instead, the sound that you select is your personal choice.
Yes. Okay, thank you. And then we have a question from Chris Bremer. Thank you for your interesting presentation, Paolo. Do you have an example where the auditive perception helped you in your interpretation?
Yes. Again, if you go to the seismic section of Screwguard, you will see that there are blank areas where the imaging is very poor in the right part of the section, in the right half of the section. In that area, we know that there are gas chimneys that cannot be seen very well from the seismic imaging, but they can be listened to very well. So in that case, the listening is more powerful than the imaging. This is a very interesting case. Another very interesting case is published by myself in one of the papers that I showed you before, where we were able to distinguish between high gas saturation from low gas saturation channels very well using only MIDI attributes. It was not possible using conventional seismic attributes, but it was possible using MIDI attributes and deep neural networks working on them.
Okay, and then we have one last comment, I think, from Edward. He says, yes, I foresee implementations of this MIDI transform and associated attributes in passive DXS monitoring with downhole fiber optics as waterfall plots can be complemented by listening to MIDI format data, monitoring induced seismicity in geothermal injection wells.
Very interesting. Yeah.
Yes. Okay, I think we don't have any more questions. I'm gonna check the Q&A. Yeah, I think we're good. So I'm gonna briefly share my screen.
I need to stop my sharing probably.
Yeah, I think.
Okay.
I
Now
think you can see my screen now.
Yeah.
Oh yeah, we finished with the Q&A. So before going to the acknowledgements, I have an announcement from EAG, and is that like the EAG Digital is the third EAG Digitalization Conference exhibition. Its technical program has been announced, and so this conference focuses on the digitalization as a key enabler to innovation and to the industry transformation needed through the energy transition. And they have four main topics that you can see here, but of course you can find more information in eagdigital.org. The conference is going to be from the 20th of March to the 22nd of March, and it's going to be in London in the UK. So yeah, you can find more information in the webpage. And yeah, finally, I would like to thank Paolo for your presentation and for your time, for agreeing to be a speaker tonight and sharing your like very creative research. And also, I would like to thank all of you for your participation tonight. Sorry, I have a online and in person. That's from another meeting. I'm sorry. But yeah, like stay tuned to our webpage and our LinkedIn webpage and also our newsletter. We are gonna soon announce like our next event once we have the dates confirmed, but that's coming soon. So thank you everyone for being here, and
thank you.
Yes, have a nice evening.
Thank you.
Thank you very much.
Thank you, Paolo. Thank you, everybody.
Thank you.
Have
Thank
a
you
nice
very much.
evening.
Bye. Ciao,
Take
ciao
care.
Diego.
Bye-bye.
Bye.
Ciao Paolo, grazie.
Grazie.
Bye.
Ciao, grazie a te. Ciao.
Bye bye.
Ciao Florenza. Bye bye.
Ciao.
Bye bye. Ciao.